Okay, so let's move on and talk about the third discrete group. And these groups are called the symmetric groups. They're also known as permutation groups, but I think I'm going to call the permutation group something slightly different. So symmetric groups, Sn. Okay, so the symmetric group Sn is defined to be the group of all permutations of n distinct objects. If they're identical, then it'll be something different. Objects is called the symmetric group. Sn. So for example, suppose you have an apple, an orange, and say a banana, and you have three boxes, say box number 1, box number 2, box number 3, right? So there are, you can have these guys, and you start with some configuration where this thing is here, this thing is here, this thing is here, and then you can have permutations of these things, right? Where you can have one where the banana stays in its place, but the orange, say, goes here, and the apple, goes, sorry, let me get rid of the banana here. But the apple goes here, and so forth, so on and so forth, right? So the operations which take you from here to here, those operations form a group. There's always going to be an operation which doesn't change it, right? It just takes it to itself, and that's going to be the identity operation. Okay. So what is the order of the group? Since how many configuration different permutations are there of n objects? So if you have n objects, so here we have 3 objects, how many different permutations can we have, like arrangements?
6.
Right. So for n objects, we have how many? Factorial n, right?
Yeah.
Factorial n permutations. So there must be factorial n. So this means that there must be factorial n distinct group elements, right? So the order of Sn must also be factorial n factorial. So it's an old habit of mine. I say n factorial. It should be factorial n. It should be n factorial. Okay. So let's give you an example. S2, which is the permutation group of 2 objects, which is, this means that 1 goes to 1, 2 goes to 2. This means that 1 goes to 2 and 2 goes to 1. Okay, so the notation is, this means that the object in place 1 goes to object in place 1, object in place 2, object in place 2 goes to object of place 2, and 1 of 2 means 1 goes to 2 and 2 goes to 1. Okay. So S2 is homomorphic. It's actually isomorphic to Z2. right? We know that all discrete groups of two elements is necessarily Z2.
Sir, what does like one bracket one like bracket two like written like this side by side mean? So
this means that there's a group element where one doesn't change its place, two doesn't change its place either.
Oh, okay.
Yeah. Yeah, there are very many different notation from symmetric groups. Okay, so this is an example, and S2 is the only abelian symmetric group.
So won't there be an element like 2 goes to 1, then goes to 2?
Sorry?
Won't there be another element? 2 goes to 1 goes to 2?
That's the same as this one, right? So that's a very good, so 2, 1, right? This is what you're saying. That's a very good question. So this is going to be, that's very, very good, is 2 goes to 1, 1 goes to 2. So we see that 1, 2 is equal to 2, 1, right? Because if I have, say, if I have an apple and an orange, then this first element is taking this to this and this to this, but this element is also doing the same thing. So they're the same element, right? 1, 2 is equal to 2, 1. And in general, if I have, for bigger symmetric groups, this is the same thing. Cyclic combinations are always the same.
Oh, understood.
Okay. Okay, so let's look at S3. Let's look at another example, S3. So order of S3 is 6, right? And so what are the elements? So for example, the identity element is just going to be 1, 2, and 3. Nothing changes, right? And then there'll be other elements such as 1, 2, 3. So for notational purposes, we shall, if an element doesn't change, we just omit it. We're going to write that as 1, 2. Okay, so this is the one that exchanges, objects in 1 and 2, right? And then similarly, we are going to have, say, 2 and 3, which exchanges objects in 2 and 3. And we can write this as 2 times 3. Similarly, we can have, say, 3 and 1 and 2 that will exchange objects in 3 and 1. That we can write as 3, 1. Okay, so we have how many elements? 1, 2, 3, 4. Okay. There's more elements. There's this element which is 1, 2, and 3. And what it does is that it takes what was in 1 to 2 to 3 to 1. So let me just do it very explicitly. So we have position 1, 2, 3 before and position 1, 2, 3 after. Suppose we had in position 1 A, B, and say C. So A will go to 2, B will go to 3, C will go to 1, right? Right? So there's another element in this group because we are up to 4 now, and that's going to be 3, 2, 1. Okay, and what will 3 to 1 do? 3 will go to the object in 3 will go to 2, it'll go to 1, and 1 will go to 3. And if we do it explicitly, then say we have 1, 2, 3, 1, 2, 3, and this is A, B, and C, then C will go to 3, C will go to 2. So C will go to 2, and B will go here, and A will go here, right? So we see that the two elements starting from the same initial configuration takes us to different configurations, right? So a few other things that I want you to note is that, so these are called cycles. So this is it's an example of a 2 cycle. Okay, so 1, 2, 3 is an example of a 3 cycle. And for a 2 cycle, Ij is equal to Ji, right? It's just exchanging of the ith and the jth element. And so Ij is equals to, so they're their own inverses, right? The other thing to note is that if you have a bigger element, like 1, 2, 3, that can always be decomposed into a smaller element. And I'm not going to prove that. If you want a general proof, Hugh Osborne has one proof in his lecture notes. It's not very illuminating in my opinion, so I'm just not going to try to do that. So this is 1, 2, 2, 3. So this one acts first and this one acts after, right? So composition. So, and you can verify that with the 3 objects that and on the other hand, we have 3, 2, 1. 3, 2, 1 can be written as, say, 3, 2 composed with 2, 1. And we saw that this guy and this guy led to different configurations, right? See? They led to different configurations. This means that 1, 2, 2, 3 is not equals to, well, 3, 2 is the same thing as 2, 3, right? So 3, 2, we can write it as 2, 3. And 2, 1, we can write it as 1, 2. So that means that this is not an abelian group. S3 is non-abelian. Okay. So I'm calling this symmetric group. You also want to call it as the permutation group. And there's a little bit of a, I think, impreciseness in the literature about what is a permutation group. So what I'm going to call permutation group is the following. In my definition, permutation groups are groups of permutations of, say, n objects, but they don't have to include, say, all possible subgroups, all possible permutations, okay? So all symmetric groups are permutation groups, but all permutation groups are not symmetric groups. So for example, the order of, say, S4 is factorial 4, which is 24. So this is the symmetric group. But it has a subgroup, say, E, which consists of E, 1, 2, and then 3, 4, and then 1, 2, 3, 4. Okay, so this is a subgroup. So this is a permutation group. This is an example of a permutation group of 4 objects. And this is kind of a subgroup of S4, right? So this is what I call a permutation, an example of a permutation group. So S4, I was doing an internet search. S4 has 30 proper subgroups. I think proper, yeah. So yeah, you can find that a listing on the internet. Okay, so each of these group is called a permutation group. Okay. Any questions?